Thank you very much for the organizers for having me. Yeah, so I'll be talking about the surprisingly rich computability theoretic content of finding discrete subspaces of Hausdorff CSC spaces. So just an outline, I'll talk about this principle GST2, which is exactly the principle of finding a discrete subspace of a Hausdorff CSC space. I'll talk about just like the standard part that you'll see in the Ginsburg-Sands paper with that was mentioned in that Damir talked about last week, and then some effectivizations that I've been studying since then. And then we'll talk about GST2 as an instant solution problem and compare it to other problems in the Weihrauch degrees. And then if there's time, I'll talk about the computable structure, this other project I'm working on involving trying to ask questions from computable structure theory and apply them for CSC spaces in particular. So here's this theorem from the paper that Damir talked about last week. This was with Heidi Benham, Reed Solomon, Java, Darlene Villano. So it's this paper, it's this theorem by Ginsburg and Sands saying that every infinite topological space has a subspace homeomorphic to one of these following topologies on the natural numbers: the indiscrete, initial segment, final segment, cofinite, or discrete topologies on the natural numbers. And we formalize this by restricting to countable second-countable spaces, which I'll refresh you on in the next slide. And I'm particularly interested in the Hausdorff case. If X is a Hausdorff topological space, CSC or not, you can't have any of these subspaces if you're Hausdorff. So you have to be discrete. So every Hausdorff space has a discrete subspace. That's what the Ginsburg-Sands theorem is saying, specifically for Hausdorff spaces. Okay, so just to refresh, countable second-countable spaces were introduced to reverse math by Francois Duret in 2011. And here's the original formalization. It is a triple XUK, where X is a countable set of points. U is a U is a sequence of basic open sets for the topology on X. It's a countable sequence, that's the second countable. And K is this function that essentially tells you the intersections of basic open points, it tells you the indices of basic open sets inside intersections of other basic open sets. That K function will play basically no role in today's talk. So CSC spaces, again, have been used for studying point topology for a while now. Francois Duret in 2011 this was specifically studying compactness. Paul Schaefer in 2020 looked at linear orders. You take a linear order, you put the order topology on it. You now have a CSC space if it's a countable linear order, and you can look at compactness for those types of spaces. And then there's the paper we just talked about. Giorgio looked at regular CSC spaces, and then most recently, David Gonzalez and I looked at CSC spaces just from like the computability theory perspective, not in reverse math, and just characterized certain index sets of countable second-countable spaces, of computable CSC spaces. Okay, so GST2 is this principle. Every Hausdorff CSC, every Hausdorff CSC space, we'll just assume it's, we can always, we're just not going to care about the case where it's an infinite CSC space, so we can just assume that it has points that are the natural numbers. Every Hausdorff CSC space has an infinite discrete subspace. I will often not remember to say infinite, but we're always looking for an infinite discrete subspace. And so actually, you can prove this in RCA knot. So initially, it might look like sort of a boring principle if you can just do it in RCA knot. I do want to go through the classic proof of it, and then I think you'll be a little surprised as to why you can prove it in RCA knot. So the classic proof looks like this. You have it doesn't have to be a Hausdorff CSC space, but it is, or it doesn't have to be a CSC space, but let's just assume it's a Hausdorff CSC space. If X is discrete, then we're done, right? Like we're trying to find a discrete subspace. Well, just use the whole space. So assume the space is not discrete, then it has a point in it called a limit point, and that is a point P where every time you draw an open set around it, you can find another point that's distinct from P. And so the rest of the proof is going to be by picture. The words are right there, though. But if you have this point P, then, well, you're in a Hausdorff space, so the first thing you want to do is look at another point and separate them with disjoint basic open sets. Okay, well, hey, I just drew an open set around P. It's a limit point, so I can find a point inside this basic open set that's disjoint, that's distinct from P, call it X1. Well, now again, I have 2 points. So within this open set, I can find 2 more open sets that are disjoint and separate them. And yet again, I've just drawn an open set around P. So again, there's another point X2 in here, and you just repeat. There's disjoint open sets here and here. There's a point in this open set, and you just continue. And what you get is this sequence of points, x0, x1, x2, x3, and so on, which turns out to be to form a discrete subspace, an infinite discrete subspace of your CSC space. So you can do this whole thing classically, right? Because you just you know your Hausdorff, so you know these open sets exist. Right, you just have this sequence of points that happens to converge to P, but it forms your discrete subspace. So I think this is a little bit surprising that you can do this in RCA not, because I didn't say anything about, so we know the space is Hausdorff, but if I give you 2 open sets, it's hard to tell whether or not they're disjoint, because you're checking for all x. Is it the case that if x is in one of them, it's not in the other, right? That's how you check if 2 points or 2 sets are disjoint, and in general, that's a pi1 statement. That's hard. You can't check that computably, right? So how can RCA not do this? Well, it turns out to do this sort of construction, you don't really need the actual disjoint open sets, but you do need essentially a delta 2 approximation to that type of function, right? So this lemma just says that if you give me, so provably in RCA not, if you have a Hausdorff CSC space, there is a function which, given 2 distinct points x and y and a number s, you can find 2 basic open sets which up to s, they look disjoint. And for sufficiently large s, this will be the pair of, this will be the 2 basic open sets. This will give you the indices of the 2 basic open sets separating x and y disjointly. Of course, you computably don't know which s you need, but you know that eventually you'll find it. And that turns out to be all you need to do this proof within RCA not. When you know that the eval limit point. Okay, but so if you don't need a delta 2 approximation, say because the space is effectively Hausdorff, so what effectively Hausdorff means is if you have 2 distinct points, there's a function that takes 2 distinct points and gives you the indices of the actual 2 basic open sets that do disjointly separate those 2 points. That's called effective Hausdorffness. We're also going to look at effective discreteness for a subspace, and subspace A is effectively discrete if there's a function D which takes points in A and tells you the index of the basic open set that isolates that point X in the subspace, right? This is the open set in the subspace topology, right? So this says X is isolated in this subspace. And so Dore knew that being a Hausdorff space being effectively Hausdorff, or a discrete space being effectively discrete, being able to prove that in general, you need ACA not. It's equivalent to ACA not, right? Essentially, you need 0 jump to find these 2 functions. Right? You can prove that you need 0 jump. Okay, I have a slight improvement, which is even if this, the previous theorem says that every discrete CSC space is effectively discrete. You don't necessarily know anything about the effective Hausdorffness. But even if the space is effectively Hausdorff, you still need ACA not to show that it's effectively discrete. The whole space is effectively discrete. And then for finding subspaces, right, the following are equivalent: ACA not and every discrete CSC space has an effectively discrete subspace. So again, RCA not proves that every Hausdorff CSC space has I shouldn't say effectively, I should just say discrete subspace. ACA not is needed to prove that every discrete CSC space has an effectively discrete subspace. And so what's missing, let's look at this principle. Every infinite discrete effectively Hausdorff CSC space has an infinite effectively discrete subspace. So again, if you want the whole space to be effectively discrete, you need ACA not. But we're just looking for an effectively discrete subspace. And we know that if you're not effectively Hausdorff, you also need ACA not. So we have this new assumption on the space that it's effectively Hausdorff, and we also have this new requirement for the subspace that it's effectively discrete. So this is like an effectivization of the Ginsburg-Sands theorem for Hausdorff spaces, hence EGST2. And so in fact, this principle turns out to not be provable in RSA not. And just to show you how this proof looks, just standing outside of reverse math and just thinking of just in plain computability theory, right? When I'm looking at a CSC space, just in plain computability theory, I can say it's computable if the basic open sets are uniformly computable and the K function is computable. X is effectively Hausdorff. Now, instead of requiring that function to exist, right, we want it to be a computable function, right? Because in general, it's a zero-jump computable function if the space is, when the space is Hausdorff. But we want the function to, in fact, be computable in order to say X is effectively Hausdorff. And then a subspace A is effectively discrete if this function that's telling you the isolating basic open sets in the subspace topology is computable. Right? Now we want that function to be computable. So just to mention, like what we just did here, right? You can totally do like computably if you know the space is not discrete, right? If you have this limit point P, then you can do this whole thing computably, right? Now you actually have in hand, oh, well, I have this point x0 and P. I just use my effective Hausdorffness function to actually find these two basic open sets, and then you just do the construction primitive recursively. Right, so I wrote here the classical proof is effective, right? But that's assuming the space is not discrete. So what about if the space is discrete? Well, in the paper, I showed that there is an infinite computable discrete and effectively Hausdorff CSV space, which has no computable infinite effectively discrete subspace. And okay, I remembered to say infinite there. So right, the hard part is, what's interesting, I think, is right, the hard part is because it's discrete. If it wasn't discrete, right, you could compute just an effectively discrete subspace. But when it is discrete, there's such a space where you can't compute one. And so just what the proof kind of looks like, I won't go through every detail, but it's a finite injury proof. You build a sequence of basic open sets, and then what we're going to do is, so like these are our basic open sets that we want to put in the CSC space. And then what we'll do is we'll take those basic open sets and we'll close it under finite intersection. And that gives us a basis and that K function for the CSC space for free. You build this with finite injury. So you have these two types of requirements. For each X, you have the requirement dx, which says that, well, there is an n such that Vn is just singleton X. This is, if we fulfill all these requirements, then we build a discrete space, right? The space is discrete if you can always find if every point is isolated. And then for each E and U, we have this requirement REU, which essentially says we don't have any infinite effectively discrete subspaces, right? So that are computable, right? So phi E is going to be the potential characteristic function of an infinite subspace, and phi U is going to be the D function that says that it's an effectively discrete subspace. So we just have to prevent phi E and phi U together witnessing that we have an effectively discrete subspace. So if we meet all these requirements, right, what does this requirement say? It says that, well, if phi E really is a total function on this infinite set Y, it's a characteristic function of this infinite set. Phi U is total on Y, then there is some point witnessing that it's not actually a success of being effectively discrete, right? You have this point X where this potential D function gives you this finite sequence of sets whose finite intersection should be singleton X, and so we just require that like not singleton X. If we can do that, then we've met REU. So if you do this, if you meet these requirements via finite injury, and then you, again, like I said earlier, close the VIs under, or the VNs under finite intersection, then you get your CSC space, which is, you commit in advance to knowing which basic open sets are going to be your witnesses to effective Hausdorffness. You can commit that in advance and still do this proof. And so it is discrete because we met all these, but it can't have any effectively discrete subspace that's computable because we met all these requirements. Okay, so just some observations. GST2 broke up into two cases. If X is discrete, then we're done. If X is not discrete, then given a limit point, we do some, turns out to be computable process and find a infinite discrete subspace. But for EGST2, the difficult case when you need more than RCA not, you need that in general when X is already discrete. Again, I just think that's very counterintuitive. So one other thing I'll mention is let SEGST2 be the restriction of EGST2 to stable CSC spaces. Those are when every basic open set is either finite or cofinite. And this, if you do this construction, if you look in the details, this actually constructs sure enough, it constructs a CSC space where all the basic open sets are either finite or cofinite. So in fact, we build a stable CSC space that's discrete and effectively Hausdorff, but with no infinite effectively discrete subspace. So actually, RCA naught doesn't even prove stable EGST2. So we've been working on trying to find upper and lower bounds of EGST2. This is joint work with Demir, Giorgio, and Paul. So RCA naught proves RT22 so RCA naught proves that RT22 implies EGST2, and for the stable version, then you will need SRT22. So this shows that, for example, it's below ACA naught, right? Because you can prove it from Ramsey for pairs, which is below ACA naught. So just to go through the proof, you have your effectively Hausdorff CSC space witnessed by H. You can always reduce to the case where every basic open set is finite or cofinite by using co, right? When you have co, you look at your sequence of basic open sets, right? Co gives you a subspace where all those, where in that subspace, all the basic open sets are finite or cofinite. So you can actually just use co to assume we're just proving a stable EGST2. And then, right, so you define some sets like this. What's going on here is you take all your points in the space, you lay them out like this. Maybe this is just 0, 1, 2, 3, 4, 5, 6, 7, and so on, right? And for each pair of points that are vertically across from each other, you can disjointly separate them using the effective Hausdorffness function, right? So this H2i, 2i plus 1 is essentially separating 0 from 1, separating 2 from 3. We know these are disjoint, we know these are disjoint. You may have something like this, right? Like we don't necessarily know anything about these, but we know that we know again that these two are disjoint and so on. So maybe it looks like this. And so on. And so these basic open sets up here are this is UP0, this is UP1, UP2, and so on. And down here, these are UQ0s, UQ1, UQ2, etc. And okay, then you define this coloring, right? This instance of RT22, C, which takes pairs I and X, assume I is less than X, and colors IX 0 if X is in UPI and 1 if X is not in UPI. And you look at an infinite homogeneous subset for this coloring, right, using RT22. If H has color 0, then what does that mean, right? It means for every I, right, there are infinite limiting X such that CIX is 0, right? Because you just look at I and X and H. And so UPI, for every I and H, that means UPI is infinite. But we're in the stable case, right? We've assumed that we're stable. So if this in the basic open set's infinite, it's actually, this should say cofinite, not co-infinite, sorry. Therefore cofinite, then QM must be finite. Why is that true? Right? If you have two basic open sets that are disjoint, then at most one can be cofinite. You can't have them both be cofinite because they're disjoint. If they were cofinite, they would intersect, right? So if I look at these two open sets right here, at least one can't be cofinite. So if one is cofinite, the other one isn't, right? Well, if H has color 0, then for all I and H, UPI is cofinite. So for each I and H, UQI is finite. So we have an infinite set of finite basic open sets, and we know that they include new points as we go along. So using B sigma 2, for example, you can find, which is provable by RT22 and SRT22, you can find an effectively discrete subspace because we know our basic open sets. They're those right there. And the proof is essentially symmetric if H has color 1, except it's right, the UPIs end up being finite because the UQIs end up being cofinite. And then this coloring is actually a stable coloring when the CSC space is stable. So this also shows that SRT22 implies stable EGST2. So those are all the upper bounds I'm willing to show the proofs of. There are some some slightly shorter upper bounds that you can ask me about if you want. And we're also working on finding lower bounds for EGST2. It's still very much work in progress. Okay, shifting gears a little bit, the next thing I'll talk about is looking at GST2 as an instant solution problem. It's a problem, right? I give you an infinite Hausdorff CSC space, and a solution to that X is any infinite discrete subspace of that space, of that CSC space. So, right, RCA naught could prove GST2, so it's true in rec. So it's a computably true principle. It's a computably true principle. But it does not uniformly admit computable solutions. What that means is there isn't one fixed phi that can, given any Hausdorff CSC space, can compute a discrete subspace of that space. So, right, what we showed is, right, what we have is for every, right, the uniformity, what this uniformity is preventing you from doing is, like, we do have that, given a Hausdorff CSC space, there is an algorithm for computing a discrete subspace based on whether it's discrete or not, right? But you can't do it uniformly. There isn't one fixed that can rule them all. And then the following lemma is helpful for doing this type of stuff. If you have you think of it as a finite binary string or a finite set, what we're looking at here is, think of it as like a finite set of pairs that are telling you membership in like the first few basic open sets for the first few many bits, right? And any point, then you can find a Hausdorff CSC space which like agrees with what sigma said about the first few basic open sets, but then extends it to a real CSC space, where every basic open set containing P is actually cofinite. Right? You can. What this is saying basically is you can tell me very late when you're building a CSC space. Oh, by the way, like 3 is a limit point. Right? Every basic open set containing it is cofinite. You can delay that very late in the game when you're constructing a CSC space, and so that's helpful for doing like forcing. And so just like the proof sketch for what you do is, suppose phi does uniformly compute like solutions to GST2. What you can do is search for any binary string sigma and any p such that phi on sigma with p Halton equals 1. What that's saying is essentially, right, you have this initial segment of a CSC space, and you have this potential limit point, right? For example, you could start with like a CSC space where you know the limit point is going to be 0, and it only has one limit point, and it's 0, right? Then you can take p to be 0, right? Then at some point, eventually, this has to tell you that, okay, fine, 0 is oh, I'm sorry. This is not for limit points yet. So this is saying P is a member of the discrete subspace. I'm sorry. So it's not a limit point, right? So eventually you have to tell me like, okay, fine, this point isn't going to be a limit. Isn't going to be a limit point. It's going to be in the discrete subspace. Well, then by the lemma, right, we can assume we can actually change our mind, right, above sigma, and say that actually that's going to be a limit point, and then that limit point can't possibly be a member of the discrete subspace. And so you diagonalize against that, right? We made every open set containing P actually be cofinite. So A intersect BY for any infinite discrete subspace A can't be singleton P because it should actually be infinite, right? If UI contains P, UI should be infinite. In fact, cofinite. Right? A cofinite set intersects a infinite set can't be finite. It has to be infinite. Okay, and then just to review Weihrauch reduction, if you have two problems P and Q, P is Weihrauch reducible to Q written this way. If there are these fixed Turing functionals phi and psi, which take, so you have a problem you have an instance X of problem P. P takes X and tells you a problem, an instance Y of Q, right? And then you have some solution Y hat to Y, and then psi should be able to take X and that solution and compute a solution X hat to X, right? And so the point is like this is uniformly turning instances of X into instances of Y, instances of P into instances of Q, and then given any solution, you can uniformly compute a solution back to the original problem. So if you think of, we can think of two other problems that were very closely related to GST2. There's the problem is discrete, which you give me an infinite Hausdorff CSC space, and I'll tell you 1 if it's discrete and 0 if it's not discrete. This is a decision problem. And then there's the lim point, which gives you give it an infinite non-discrete Hausdorff CSC space, so it must have a limit point. So then the solutions are just any limit point of the space. And so if you go through the proof of GST2, right? How did we prove GST2? Well, we started by asking, is the space discrete? If yes, then we're basically done. If it's not discrete, well, give me a limit point, and then do this computably, and you're done, right? So this is composition. This is the compositional product for Weihrauch problems, for instant solution problems. But it just says, right, solve is discrete, and then solve limit point. And so GST2 is reducible to the problem of first checking if it's discrete, and then finding a limit point. Okay. But it turns out the limit point is not Weihrauch reducible to GST2. And what the proof looks like for this is, it looks kind of like forcing. So you have, right, suppose that limit point does reduce to GST2, right? So you have these functionals phi and c. Okay, search for finite sets x0 prime and d0 prime, where psi of x0 prime join d0 prime is 0. Why can you do this? It's because you can take, like x0 can be a CSC space that has exactly one limit point, 0, right? That's an instance of limit point. Then phi of x0, right, is some other instance of GST2. It has some solution in GST2, and that tells you, right, which is the discrete, it tells you that has some solution d0, right? D0 is going to be like the discrete subspace of phi of x0, right? And then C should be able to take x0 and d0 and tell you, okay, fine, well, 0 then was a limit point of x0. Okay. Yeah, 0 should be the unique limit point of x0. Right? Okay, and so like since those two things exist, like you can computably search for finite sets, like finite initial segments of those essentially, where, okay, well on this, like you only need this much information to conclude, okay, 0 was a limit point of phi of x0. Okay, and then d0 prime, right, is just gonna be this finite collection of points. Then, okay, if x is any instance of limit point, extending this finite, this should be x0 prime here, x0 prime, then, and x doesn't have 0 as a limit point, and something else as a limit point, right? But since x extends x0, right, psi of x join d0 prime still halts and gives you 0. So what this is telling you, like, right, is like d0 prime can't be the initial segment of any infinite discrete subspace of phi of x, because if it was, d0 prime would be part of the solution, right? It'd be the initial segment of a solution, and then C should tell you an actual limit point, but 0 isn't the limit point, right? Okay, well then, if d0 prime can't be an initial segment of an infinite discrete subspace of phi of x, then one of those yi's needs to actually be a limit point of phi of x. And then you just go and show, well, if I have a limit point of phi of x, then there's this functional delta, which given a limit point to phi of x, I can find a limit point of x. And right, you can write down this functional exists if phi and psi exist. I won't write it down, but it uses the fact that you can do this sort of thing computably. And then, well, you only have these finite collection of limit points to worry about, and you just diagonalize against any of those actually being a limit point of x. So you extend like n more times essentially, and diagonalize against each one of these being a possible limit point of phi of x. Okay, so that's what we just showed. And so that actually means that GST2 is strictly Weihrauch below limit point composed is discrete. Which I think is very interesting, because like, how else do you prove GST2, right? You check if it's discrete, and if it's not, you would have a limit point, and then you do this. So it seems very natural that, like, to me, I was expecting these to be Weihrauch equivalent, but they're not. It's not. Like, you can't do that. Like, lim point only takes non-discrete Hausdorff CSC spaces. Yeah. Well, it is, but it only takes in. It's restricted to just non-discrete. Like they always have limit points. You only give it a Hausdorff space with a limit point. Yeah. Like it's not like immediately. Yeah, but like it's yeah. Okay, and then we wanted to like we can also characterize limit point and is discrete in terms of some other known problems. So like you can see in this paper with David Gonzalez, right? Having a limit point is a sigma 3 complete property of Hausdorff CSC spaces. So you can actually formulate lim point and is discrete using that information in terms of other known problems. So lim point is Weihrauch equivalent to the jump of choice on the naturals, which is essentially the problem of here's a non-empty pi2 set, give me an element of that set. And is discrete is Weihrauch equivalent to the strong total continuation of the double jump of choice on one element. What that is essentially, I mean, it's this thing. Technically, it's even more complicated than that, but it's essentially just like here's a pi3 statement: is it true or false, right? Right? Because what's pi3? Well, being discrete is pi3 because having a limit point is sigma 3 complete. So the completeness tells you that it's exactly the strength of this problem. I just think it's really cool that like there's a connection from like index sets to like being able to prove things by Weihrauch stuff. Okay, this time, so I'm going to talk a little bit about computable structure theory for CSC spaces. This will segue nicely into Java's talk about computable structure theory. Okay, so computable structure theorists have this notion of computable dimension and computable categoricity. So the weak computable dimension of a CSC space is going to be the number of computable copies of X up to computable isomorphism. This should say like computable homeomorphism for us, right? Homeomorphism is the isomorphism we care about in for topological spaces. And then weakly computably categorical, your X is weakly computably categorical if there's only one computable copy of X up to computable homeomorphism. Now, what do I mean by computable homeomorphism? I'm literally just mean a homeomorphism that happens to be a computable function on like natural numbers. Not at all. Yeah, so the K function doesn't play a role so much in this case either. Yeah, I haven't thought about that actually. So I've been thinking, so again, I do mean.
I look at them as structure.
Well, it's hard to do that. It's hard to do that, right? Because. Oh, okay, even better. Yeah, I mean, it's just like the K function very literal, very infrequently. Very infrequently, the K function plays a role. What I'll just say is, again, like what makes homeomorphisms more complicated than just like isomorphism is right, you're not just preserving some relations and functions. Like you actually have to like the preimage of a basic open set needs to be open. It doesn't have to be like a basic open set either. It could be the union of the countable union of some basic open set. So computable homeomorphisms are in general a lot more complicated than like isomorphisms. Like for traditional computable structures. And so actually, the discrete topology is weakly computably categorical, because if you give me some other CSC space that happens to be discrete, like the identity function on the naturals happens to be a homeomorphism between those two spaces, right? Because the preimage of every basic open set is open just because everything's open in the discrete topology. But we've seen, right, that the presentation of the CSC space can change a lot about the CSC space, like whether or not it's effectively discrete. And so we like our notion of isomorphism or homeomorphism to like preserve effective discreteness, for example, or like the other like computability theoretic notion, like facts about our CSC spaces. So Dray defined the notion of effectively continuous, which has this formal definition, but it's really just so it's this, look, all that's going on here is you have your two CSC spaces, X, Y. You know that your function takes X to f of X, right? F is some function. What is it for me? What is it to be effectively continuous? Well, it's going to be computable. And, right, what we have is, right, the preimage of a basic open set needs to be open, right? So if we know that f of X is in some basic open set VI, right, then the preimage of VI had better be an open set, not necessarily open, but it had better not necessarily basic. But the preimage of VI had better be an open set over here containing X, right? But moreover, right, since this is an open set, right, there is a basic open set in here containing X, call it Uj, right? And all we want is there should be a uniform way of taking X, which is in VI, and telling you, oh, well, it's in Uj, which is this basic open set contained in the preimage of VI under F, right? So given X and I, you can uniformly compute this J. That's what it means to be effectively continuous. And then being an effective homeomorphism is just your bijection. That's where both the F and its inverse are effectively continuous. So this is actually the notion of like isomorphism, the computable isomorphism that we'll use for CSC spaces. So given a CSC space X, the computable dimension of X is actually the number of computable copies of X up to effective homeomorphism. And X is computably categorical if it has computable dimension 1. So up to effective homeomorphism, there's exactly 1 copy. Weak computable dimension. And so what we want to show as well is we know already, right? Well, actually, don't. Never mind. Let me not get too far ahead of myself. So given a CSC space X, assume it's discrete. Right? A discreteness function for that CSC space is this function D that just tells you the isolating basic open sets for each point in X. Right? It's like the witness to the space being effectively discrete. It may not be computable if the space is not effectively discrete. But if I have X and Y that are effectively homeomorphic, and I give you a discreteness function for X, then Y has a discreteness function computable from dx. Right? And so in particular, if X is effectively discrete, then so is Y. Right? And so this is, again, why I think effective homeomorphisms are good, right? Because you can have plenty of homeomorphic copies of the discrete topology, some of them are effectively discrete, some of them aren't, right? But if they're all effectively homeomorphic, then they're either all effectively discrete or not. And so actually, so for each, right, this is technical lemma. For each E, there is a computable, like uniformly in E, computable discrete CSC space, such that the unique discreteness function, XE has a unique discreteness function, call it DE, and DE has exactly the same Turing degree as the domain of the E partial computable function, right, the ECE set. And since they're antichains of this, right, you can have an infinite collection of discrete CSC spaces, none of whom are effectively discrete because none of whom compute discreteness functions for each other. So the discrete topology is actually computable dimension omega. So it's certainly not computably categorical, but in fact it has computable dimension omega. Okay, that's it. Thank you.